What would happen if, in just the next few minutes, the way you look at Earth began to change? Even though Earth itself does not move at all, not by leaving the planet immediately, and not through overwhelming numbers or familiar dramatic images. This journey begins with a very small change in perspective. Not a leap away from Earth, and not the act of placing this planet alongside familiar celestial bodies like the Sun or Jupiter. The starting point is a simpler, but more precise concept: true scale. At that scale, Earth doesn't just become smaller, it becomes hard to recognize. Like an extremely fine detail in a picture so vast that the human eye isn't used to searching for it. When it comes to the true scale of the universe, the first thing that appears isn't a number, but a feeling that's difficult to put into words. Earth isn't just smaller than imagined. It's so small that finding the right language to describe it becomes awkward. Familiar ideas of big and small begin to lose their clear boundaries. In this frame of reference, the familiar planet, where life unfolds every day, no longer holds a central position. It slowly recedes, until it nearly blends into the vast, dark background around it. This journey isn't meant to create awe. It simply opens up a different point of view. When the perspective changes, the same object carries a different meaning. Not because the object itself has changed, but because the frame of reference is no longer the same. When the journey ends, Earth and humanity's place may be seen in a different light. Not new in a sensational way, but different in being quieter, more distant, and more panoramic. Before going that far, it's necessary to pause at the most familiar place of all, right at Earth's surface. From here, everything looks very different. Standing on the ground, Earth doesn't feel small at all. It stretches out in every direction the eye can see. Continents span multiple time zones. Oceans cover most of the surface, connecting deep blue expanses from one horizon to another. An entire lifetime can pass through travel and still leave countless places never visited. In everyday experience, Earth carries the shape of vastness. Distance is felt in travel time. A long trip requires preparation. A tall mountain is a challenge. An ocean is a clear boundary. These limits create the sense that the world is large enough to hold every human story, and still leave plenty of unexplored space. If we rewind time far enough, that feeling becomes even clearer. For the first humans, Earth wasn't just a place to live. It was the entirety of known reality. There were no global maps, no images taken from above, no concept of a planet floating in space. The ground beneath their feet seemed flat and endlessly extended. The sky above felt like a vast dome, where stars appeared each night as fixed points of light, then vanished when a new day began. From that point of view, Earth didn't need to be compared to anything else. It was everything. All motion in the sky was observed from the same standing point, repeating in familiar rhythms. What could be seen shaped the entire worldview, and within those limits, placing Earth at the center of everything made complete sense. Even today, when science has expanded our view far beyond that, the feeling still exists in simple experiences. When looking toward the horizon, Earth's surface still appears flat. The planet's curvature is too subtle to notice from human height. The eyes see a plane stretching outward, and the brain automatically accepts that image as an intuitive truth. Only when we begin to measure, compare, and place Earth within different scales does the meaning of the word big start to change. Not because Earth shrinks, but because the picture around it expands. Numbers appear not to impress, but to help us imagine. When a distance is translated into walking time, or a size is set beside a familiar object, scale begins to become clearer. At the human scale, Earth truly is large. Walking steadily around the equator could take many years. Spending even a very brief moment on each small part of the planet's surface, the total time would still stretch beyond an ordinary lifetime. These comparisons don't make Earth smaller. They simply confirm that, within direct experience. This planet is vast enough to make humans feel they are living in a very large world. But right here, a subtle shift begins to take shape. When measurements are placed side by side, when Earth is compared with other objects in space, the familiar scale gradually stops fitting. Distances once considered far begin to seem modest. Sizes once considered enormous start to lose their special status. This change doesn't happen suddenly. It's like stepping back a few paces to see an entire room. The objects don't disappear, but the relationships between them change. Earth, in this new context, is no longer the foundation that contains everything, but becomes one part of a much larger collection. All of this begins with something very simple: changing the measuring stick. At human eye level, Earth is a vast, complex, and complete world. At a broader scale, the meaning of that vastness begins to be redefined, not to deny human experience, but to place it in its proper position within a larger picture. From this sense of familiarity, the journey will continue slowly. Earth will be measured using the very scales tied to human life, to understand why it once was, and still is, experienced as so large. And only after that familiarity is preserved will the process of shrinking begin, not by taking away the value of this planet, but by gradually expanding the space around it, little by little. Before Earth is reduced within larger comparisons, there is one step that must remain intact. That step is to look at the planet exactly as humans are still living on it, not through feeling, but through numbers concrete enough to anchor perception back to reality. At this scale, Earth is not vague. It appears as a very clearly defined mass, large enough to exhaust people who try to traverse it completely. Starting with the most basic dimension, Earth has a diameter of about 7,926 miles. On its own, that number does not say much, but it establishes a clear physical limit to the space humans inhabit. It is the distance from one end of the planet to the other, passing through its widest point, a distance that cannot be directly perceived by sight, yet large enough to make every movement across the surface significant. From that diameter, one can imagine the circumference. Earth's equator is about 25,000 miles long. If someone were to imagine walking around the equator, maintaining a steady pace of about 3 miles per hour, walking 8 hours a day, without long breaks, the journey would last more than 3 years. 3 years and roughly another month. Each day would cover a familiar distance. But the total time accumulated far exceeds the kinds of journeys typical of a human life. Throughout that entire period, the walker would never leave the same planet. There would be no journey through space, no change of celestial body, just walking around a circle so large that it must be measured in years. At this scale, Earth is not a small point. It is a surface vast enough to consume a portion of a lifetime. If the view expands from the equator to the entire surface, the numbers grow even larger. Earth's surface area is about 197 million square miles. This is the total area where humans can stand, move, build, and live. To picture this scale, one can use a very slow comparison. If exactly 1 second were spent on each square mile, without rest or sleep, the total time required would exceed 6 continuous years. 6 years just to skim across every small piece of the planet's surface, with each piece touched for only 1 second. This comparison is not meant to impress. It simply shows that, on a human scale, Earth is a space so vast that time becomes a more appropriate unit of measure than distance. Even countries considered large occupy only a small fraction of this whole. The United States, one of the largest countries by area, covers about 3.8 million square miles. When placed next to Earth's total surface area of 197 million square miles, it accounts for less than 2%. The rest is ocean, other continents, and regions that most humans have never set foot on. These comparisons clarify one simple fact. Within the scope of lived experience, Earth is truly large. It is large enough to contain many different civilizations. Large enough to create the sense that the world is expansive and difficult to grasp as a whole. Every map, every journey, every idea of far and near in daily life is built on this foundation. For this reason, the feeling that Earth is everything is not a mistake. It is the direct result of living on the surface of a planet that is large relative to humans. Eyes see the horizon. Feet feel long distances. Time is used to measure space. At this scale, everything makes sense, but numbers have only one role. They do not stop at description. They open the door to comparison. And with just a very small step back in perspective, these familiar numbers begin to change their role. Not to make Earth immediately small, but to place it within a different context. As the viewpoint pulls back slightly, Earth is no longer the entirety of existing space. It becomes an object with a defined size, situated among other objects that can also be measured. Here, large is no longer absolute. It becomes relative, depending on what it is compared against. This shift does not take anything away from human experience. Distances are still long. Oceans are still vast. The years required to walk around the equator still demand a portion of a lifetime. But at the same time, another layer of awareness begins to form. This layer allows Earth to be placed beside other objects, revealing that its familiar vastness exists only within a particular frame of reference. At this point in the journey, there is no need to go far. It is enough to hold on to the numbers already introduced and allow them to remain still for a moment. Diameter, circumference, surface area, time. All of them say the same thing. By human measures, Earth is a world so large it cannot be fully traversed within a single lifetime, and it is precisely from this foundation that the next step gains meaning. When we begin to look toward other objects in space, these familiar numbers will not disappear. They will remain as points of reference, so that when Earth begins to shrink within larger pictures, the change does not cause disorientation, but unfolds slowly, with clear grounding. The first zoom outward will not take the journey to distant reaches. It leads only to a very nearby place, a familiar neighbor. There, it is not the size of the objects that stands out, but the space between them. And it is that emptiness that will begin to reveal what truly dominates space. We don't need to leave the familiar region around Earth yet. Just stopping at our closest companion in the night sky and looking at it with properly scaled numbers is enough to reveal something very different. The space around us is not full, the way our eyes tend to suggest, but is mostly empty. Between Earth and the Moon, the average distance is about 855 miles. If we use Earth's equator as a reference, that length is equivalent to driving around the equator about 9.5 times. One trip around the planet is already a large number. Nearly 10 such loops, lined up into a straight line between two celestial bodies, shows just how wide this distance is, and how hard it is to connect it to everyday experience. When the Apollo astronauts headed toward the Moon, it took them about 3 days to cover that distance. Even with the rocket technology of that era, 3 days is not very long compared to deeper space journeys. But it is not a small number either. It sits in between, long enough for the brain to accept that this is a distant trip, yet still within a range that humans can fully imagine and recount. The Moon itself, if we look only at its size, is not especially large by cosmic standards. It has a diameter of about 159 miles, or roughly 27% of Earth's diameter. A simple comparison is often used. If Earth were the size of a basketball, the Moon would be about the size of a tennis ball. The difference is clear enough that the two bodies cannot be confused. but not so extreme that the moon becomes a tiny, insignificant dot. What surprises many people is not the moon's size, but the emptiness between it and Earth. That distance of 855 miles is nearly equal to 30 Earth diameters. If you imagine stacking 30 Earths in a line between Earth and the moon, most of the space in that line would be empty, not matter. This ratio shows that celestial bodies, even when they share the same home neighborhood, are still much farther apart than our initial intuition suggests. One reason this distance is often misunderstood is the way illustrations are drawn in books, posters, and simplified diagrams. Earth and the moon are usually placed close together so they fit in the frame, are easy to see, and don't require stretching too far across a page or a screen. As a result, our eyes get used to seeing two circles almost touching, while in reality, if drawn to scale, those circles would be very small, and the empty space between them would take up most of the image. From a cosmological perspective, the Earth-Moon system has a fairly unusual feature. Compared to the size of its parent planet, the Moon is relatively large. In some discussions, it has even been suggested that this system could be thought of as a kind of binary system, where the planet and its satellite have more comparable sizes than many other pairs in the solar system. Although the term double planet is not an official classification, it hints that the relationship between Earth and the Moon is more than just a large body dragging a much smaller one along in orbit. The Moon's presence is not merely aesthetic in the night sky. It has a direct and far-reaching impact on Earth. The gravitational interaction between the two bodies creates tides, causing the oceans to rise and fall continuously. These cycles help regulate temperature, move nutrients through the water, and affect many forms of life along coastlines. It is a steady, repeating motion, yet one that is deeply tied to the structure of life on the planet. Beyond tides, the Moon also helps stabilize Earth's axial tilt. That tilt determines the seasons, and its stability allows the climate to remain within a relatively comfortable range over long periods of time. Without the Moon, or if it were much smaller, Earth's axis could wobble more dramatically. Large changes in tilt could lead to extreme climate shifts, making the environment far less stable for the development of complex life. Looking back at all of this, we can see that even in a region very close to Earth, two parallel realities exist. On one hand, there is a vast emptiness between Earth and the Moon, so large that it takes multiple trips around the equator just to picture it. On the other hand, there is a tight connection through gravity, tides, axial tilt, and climate. Emptiness and connection coexist within the same system. From the perspective of this journey, what matters is not memorizing every number, but becoming familiar with the scale they suggest. A distance that takes 3 days to fly, a length equal to nearly 10 trips around the equator, a ratio of 30 planetary diameters. All of it points to the same idea. Even between Earth and its closest neighbor, most of space is empty. Once that emptiness becomes clear in this familiar home yard, I think stations. Attention drifts toward the primary source of light Earth depends on, the sun. At that scale, size and distance will continue to change in meaning, and Earth will begin to shrink in a way that is hard to undo once you have seen it even once. There is an object in the solar system that makes every number associated with Earth feel fragile the moment it is placed beside it. That object is the sun. From the surface of Earth, the sun appears as a familiar bright disk, rising each morning and setting each evening, repeating so slowly and regularly that it is sometimes almost forgotten. But if we step away from that everyday perception and look at its true size, the scale immediately reverses. The sun has a diameter of about 864,000 miles, roughly 109 times wider than Earth. If Earth were the size of a small ping-pong ball, the Sun, at the same scale, would be a massive sphere taller than a standing person. In that frame, Earth is no longer the backdrop of the story, but merely a tiny dot orbiting a large, luminous mass of gas, quiet and steady. When volume is considered, the difference becomes even more striking. With that size, in purely geometric terms, the Sun could contain about 1.3 million Earths. Not a few times, not a few hundred times, but more than 1 million spheres the size of this planet. Everything happening on Earth's surface, cities, mountains, oceans, climate, the entire history of humanity exists only on a thin outer layer of one of those spheres. This image is not meant to overwhelm, but simply to reset a basic sense of scale. What feels familiar in daily life occupies an extremely small portion when compared to the imagined volume of an ordinary star. If we shift from size to mass, the Sun becomes even more dominant. Nearly the entire mass of the solar system, when added together, resides within the Sun. About 86% of the total mass belongs to this star, while all the planets, moons, and smaller objects combined make up only the remaining 14%. In this picture, Earth is not a counterweight, but one of many small particles orbiting a central body. Every orbit, every motion, every seasonal cycle on Earth is determined by the gravitational field of an object that holds almost all the system's mass. The sense that Earth is everything, so natural at the human scale, becomes very light when placed against the scale of mass. The distance between Earth and the Sun carries its own kind of proportion. This average distance is called 1 astronomical unit, roughly 93 million miles. Light, the fastest thing in the universe, still needs about 8 minutes and 20 seconds to travel that distance. What we see each morning, as the sky gradually brightens, is actually the result of a journey that began more than 8 minutes earlier on the Sun's surface. When we think about all the signals and streams of energy moving through space in that slow but continuous way, the Sun no longer feels like a flat circle on the sky, but a distant source, constantly sending information with a quiet delay. By the standards of human transportation, a distance of 93 million miles is almost impossible to bridge. A car traveling at a steady highway speed, if it could drive along an imaginary straight road toward the Sun, would need more than a century and a half, around 170 years, to reach it. Even the fastest spacecraft humans have ever launched, such as the Parker Solar Probe, moving at hundreds of thousands of miles per hour, still take many months to approach the region near the Sun. These numbers are not meant to impress, but simply to clarify that even within a single system, distances already far exceed the intuitions of everyday life. Despite its immense size and influence within the solar system, the Sun is classified as an ordinary star. It belongs to the G-type main sequence category, sometimes called a yellow dwarf. The Sun is about 4.6 billion years old, and according to current models, it can continue burning in a relatively stable state for another 5 billion years or so. This means Earth is orbiting a middle-aged star, neither very young nor very old, maintaining a steady energy output over spans of time that are enormous compared to a human lifespan. In the larger picture of the galaxy, the Sun is not remarkable, but simply one normal point of light on a spiral arm of the Milky Way. Deep inside the Sun, every passing second is accompanied by immense energy processes. About 600 million tons of hydrogen are converted into helium in the core through nuclear fusion. A very small fraction of that mass is transformed into energy, which then slowly makes its way outward through many layers before escaping into space as radiation. The amount of energy the Sun emits in just 1 second far exceeds the total energy humanity has used throughout its entire history. Yet, at a distance of 93 million miles, Only a tiny fraction of that energy reaches Earth's surface, enough to keep the planet warm, illuminated, and climatically active, without pushing everything into extreme conditions. The conditions at the Sun's surface and core are unlike anything that can be directly experienced on Earth. Its surface temperature is about 10,000 degrees Fahrenheit, while the core reaches roughly 27 million degrees Fahrenheit. The pressure at the Sun's center is about 260 billion times greater than atmospheric pressure at Earth's surface. These numbers are difficult to attach to any concrete image from daily life, but they illustrate the vast gap between the familiar environment of a small rocky planet and the environment where the energy of an entire system is generated. At this scale, the Sun resembles a massive engine room operating continuously, while Earth is just a small chamber far away, receiving a steady portion of the energy that falls outward. The Sun is also not completely quiet. On its surface and in its outer atmosphere, there are intense events such as solar flares and coronal mass ejections. Streams of charged particles are hurled into space, carried along by the solar system's magnetic field, sometimes interacting with Earth's magnetic field. When these particles enter regions near the poles, they can produce slowly shifting lights in the night sky, known as auroras. At the same time, these disturbances can affect satellites, communication signals, or power grids. In this picture, the Sun is both a stable source of light and a quiet source of variability to which technological systems must subtly adapt. For a long portion of history, the Sun was understood within a different framework. In the geocentric model, Earth was considered the center, and the Sun was just one of many objects circling around it. This view matched what could be seen with the naked eye. The Sun rises on one side of the sky, sets on the other, and repeats this pattern each day with remarkable regularity. Only when thinkers like Copernicus proposed a sun-centered model, and Galileo later observed and defended those ideas, were the positions of the solar system's bodies rearranged. Earth stepped down from the throne at the center of the picture and became a planet orbiting the Sun like the others. This shift in perspective did not make Earth less important in everyday life, but it opened a new sense of humility before the scale of the universe. Instead of standing at the center, the planet came to be seen as a small, rocky body lying within the influence of an ordinary star. What had once seemed fixed began to be placed within a broader and quieter context. From this viewpoint, returning attention to Earth is not a diminishing act, but simply an acknowledgement that every story unfolds on a small point within a much larger structure. From this central reference point of the Sun, the picture of the solar system can gradually expand. Once the Sun is placed correctly in scale, the surrounding planets no longer appear as isolated points, but as small particles moving through a space that is mostly empty. Within that structure, Earth is just a stable, rocky dot, slowly traveling along its orbit, waiting to be viewed within even wider scales, where the sense of emptiness becomes increasingly clear. Now the journey slowly passes through the region near the Sun, where 4 rocky planets cluster like a small group surrounding the central flame. At this distance, space is still silent, yet the worlds themselves are profoundly different. Mercury orbits very close to the Sun, small and bare. Venus is nearly a twin sister to Earth in size, but its surface is a place where humans could not stand. Earth appears as a blue marble with white clouds drifting slowly. Positioned at just the right distance for water to remain liquid, Mars lies farther out, colder, pale red, carrying traces of rivers that once flowed. This entire cluster resembles a quiet experimental strip of the universe, where the same kind of solid material produces very different outcomes simply because of distance from the Sun and a few subtle conditions. Mercury is the world closest to the Sun. It is small, dark when its far side faces the star, and intensely bright when turned directly toward the heat source. With almost no atmosphere to retain warmth or provide protection, Mercury's surface experiences extreme temperature swing. Daytime heat, hot enough to melt metal. Nighttime cold, so deep that everything seems frozen solid. It completes an orbit around the Sun in about 88 Earth days. Yet it takes roughly 176 days for the Sun to complete a full cycle across its sky. There. A solar day is longer than an entire orbital year. This slow and unusual cycle makes Mercury feel like a world that both spins and wobbles, quietly enduring light and darkness without any atmospheric layer to soften the extremes. These traits make Mercury a very quiet illustration of how close is too close. It is not far enough to allow its surface to cool evenly, nor massive enough to hold onto a thick atmosphere. Instead of being a place that could sustain liquid water, Mercury is a bare rock, heated by the Sun and then abandoned to long, freezing nights. Between these extremes, there is no gentle transitional zone for familiar life. In a system, sometimes moving just a little too close to the center strips away nearly all possibilities for balance. Just beyond Mercury lies Venus, similar in diameter to Earth, yet utterly different at the surface. Beneath its thick cloud layers, Venus's atmosphere consists mostly of CO2, with surface pressure about 90 times that of Earth's atmosphere. Surface temperatures climb to nearly 900 degrees Fahrenheit, hot enough to melt metal and keep ordinary materials glowing red hot. The clouds above are not light water vapor, but contain particles of sulfuric acid, forming a dense, opaque shroud. There, the sky is not blue, and the ground offers no place that is cool. What is striking is that Venus lies farther from the Sun than Mercury, yet it is hotter. The reason is an extreme greenhouse effect. Solar radiation enters the dense atmosphere, is absorbed, and trapped inside, preventing heat from escaping easily. Over immense spans of time, this process accumulates, turning a planet nearly Earth-sized into something like a massive furnace, silent and suffocating. Distance, in this case, is not the only factor determining comfort. Atmospheric composition, surface structure, and how energy is retained also play decisive roles, transforming a planet with potential into a place with no habitable zone. Venus also has another slow peculiarity. It rotates very slowly and in the opposite direction of most other planets. A full rotation on its axis takes about 243 Earth days, longer than its orbit around the Sun. Standing on the surface of Venus, the Sun would follow an unusual path, rising in the west and setting in the east. The sky would brighten and darken according to a rhythm completely unlike the familiar day-night cycle. All of this creates the sense of a world where time moves very slowly, yet without gentleness. Like a clock running backward in a room that is always hot. Farther out, Mars drifts along its orbit, colder and dimmer. A Martian year lasts about 687 Earth days, causing seasons to stretch longer and climate changes to unfold more slowly. Its surface bears the marks of dry riverbeds, ancient shorelines, and sediment layers that show liquid water once flowed there. Today, Mars's atmosphere is thin and cold, insufficient to retain heat for long, and unable to maintain pressure suitable for liquid water at the surface. Many lines of evidence suggest Mars once had a strong magnetic field, but over time it weakened and nearly vanished. Without magnetic protection, the solar wind, a stream of high-energy particles, gradually stripped the atmosphere from the planet's surface. The result is a dry, cold world, with an atmosphere so thin it cannot hold warmth the way Earth still does. Seasons still exist. Polar ice caps still melt and refreeze in cycles. But the entire system operates within a much narrower range. Mars resembles a slower, colder, dimmer version of Earth, where the loss of protective layers happened long ago and cannot be reversed. Looking at it, one can see another version of a rocky planet, where a few very slight changes led to a completely different outcome for life. Orbiting Mars are two small moons, Phobos and Deimos. Phobos is only about 14 miles in diameter. So small it resembles a large rock, more than a moon in the familiar sense. It orbits Mars so quickly that within a single Martian day, Phobos crosses the sky 3 times. Rising and setting again and again, its orbit is slowly decaying inward, meaning that over extremely long periods, it is gradually approaching the planet's surface. Estimates suggest that in about 50 million years, Phobos may collide with Mars or be torn apart, spreading into a ring of debris around the planet. On a human timescale, this future is impossibly distant, but in the rhythm of the universe, it is simply something already set in motion, unfolding slowly, without noise. Amid all these worlds, Earth occupies a position where many factors are quietly balanced at once. Its atmosphere is thick enough to reduce temperature differences between day and night, yet not so thick as to become suffocating. A magnetic field surrounds the planet like a shield, deflecting most high-energy particles from the solar wind and preventing the atmosphere from being gradually stripped away. Its distance from the Sun is close enough to prevent all water from freezing, yet far enough to stop it from evaporating entirely. Temperature variations still exist, with summers and winters, but the range is far smaller than on Mercury or Mars. Within this framework, the conditions for liquid water and a stable atmosphere form a very quiet foundation for complex life to develop. Looking back at all 4 rocky planets, one clear pattern emerges without needing emphasis: size, though important, is not the only factor that determines whether a world can be habitable. Venus is nearly Earth-sized but too hot. Mercury is much smaller, yet too close. Mars lies farther out, cold and slowly losing its atmosphere. Only Earth sits at a distance where water can remain liquid. The atmosphere is thick enough, and the magnetic field strong enough. In a system of rocky planets, it is not the largest or smallest that holds the special role, but the one that happens to lie within a very narrow range of distance and conditions. As the inner rocky planets gradually fade behind us in this imagined journey, another region begins to appear ahead. This is the area often exaggerated in movies and illustrations, where floating rocks are drawn packed tightly together, constantly colliding. In reality, even in what is considered an asteroid-filled region, empty space still dominates. In many parts of the universe, what can be seen amounts to only tiny points, and everything else is vast, silent space, where objects continue to drift slowly without needing to draw attention. Between the region of rocky planets and the domain of the gas giants lies a long, sparse buffer zone, where the familiar human image of a space filled with objects begins to dissolve. This is where the asteroid belt is located, often portrayed in movies as a dense field of rocks where spacecraft must weave through closely packed drifting boulders. In reality, this region is far quieter. There are countless fragments of rock and material of all sizes, but the average distance between them is very large. A ship passing through this area could travel for hours, even days, without seeing a single rock with the naked eye. Space, once again, reinforces a simple idea. Places described as crowded in space are, most of the time, still mostly empty. Within that scattered region is one object more distinct than the rest, large enough to pull itself into a nearly spherical shape. That object is Ceres, a small world about 588 miles in diameter, classified as a dwarf planet. From afar, Ceres is not as striking as the larger planets, just a dark sphere quietly rotating in the void. But when the Dawn spacecraft visited it between 2015 and 2018, intriguing signs gradually appeared, bright streaks on the surface, regions that may contain salts, and evidence suggesting that beneath the rocky crust there could be a subsurface ocean. The total amount of water there, if released, could exceed the amount of water in all the rivers and lakes on Earth's surface. On a small and dim world like Ceres, the idea of a hidden sea is a reminder that sometimes the most important reserves are not found on the visible surface. Farther out, the journey reaches a world whose scale begins to blur Earth in the imagination. Jupiter is the largest planet in the solar system, with a diameter of about 881 miles, roughly 11 times wider than Earth. By volume alone, Jupiter could contain about 321 Earths. Its mass is greater than the combined mass of all the other planets put together. In the outer region of the solar system, it truly resembles a giant king, dominating the orbits of many surrounding objects through its gravity. Yet even at that size, Jupiter is still only a small sphere compared to the Sun, and the Sun itself is just an ordinary star among countless others. Each time the scale is expanded, what once seemed to dominate everything becomes just a small part of a larger layer. Jupiter's powerful gravity not only holds on to its own moons, but also affects countless fragments drifting through space. Many asteroids and comets that enter Jupiter's sphere of influence can have their orbits bent, be captured, or be flung off in another direction. Some hypotheses suggest that this role causes Jupiter to act like a cosmic vacuum cleaner, reducing the number of objects that could become collision threats to the inner planets, including Earth. Not every impact is prevented, and not every orbit is cleared, but over very long periods. The presence of such a massive planet may have reduced the frequency of major impacts in the inner system. For a small, life-rich planet, having such a gravitational neighbor farther out may be a form of quiet protection. On Jupiter's turbulent surface, there is a structure that has been observed for at least 4 centuries, the Great Red Spot. It is a massive swirling storm larger than Earth, persisting within the thick atmosphere. Winds inside the storm can reach speeds of about 400 miles per hour, forming a long-lived vortex that has maintained its basic structure across many generations of observation. However, recent images show that the Great Red Spot is slowly shrinking. About 100 years ago, it was nearly 3 times wider than Earth. Today, its size is only about 3 times Earth's diameter. No one knows exactly when this storm will dissipate, but it is possible that it will disappear within the next few generations. A phenomenon once considered permanent on Jupiter's surface is, in reality, just one phase in the slow life cycle of a layer of gas. Surrounding Jupiter is a rich system of moons, with at least 95 satellites discovered so far. The 4 largest moons, known as the Galilean moons, are each worlds of their own. Io is a place of intense volcanic activity, with constant eruptions that continually resurface the landscape with new material. Europa is covered by a bright layer of ice, beneath which there may be a deep ocean of liquid water, possibly containing twice as much water as all of Earth's oceans combined. Ganymede is so large that its diameter exceeds that of Mercury, making it the largest moon in the solar system. Callisto has an ancient appearance, heavily cratered, like a quiet archive of events spanning billions of years. Around a giant gas planet, these child worlds revolve silently, each preserving its own version of physical conditions, suggesting that the concept of a planet is sometimes just a convenient classification. A little farther out, Saturn appears, smaller than Jupiter, but still enormous. Its diameter is about 367 miles, and its internal volume could contain roughly 764 Earths. Saturn is also a gas planet, with such low density that, if there were an ocean large and deep enough, it could float. But what makes Saturn most recognizable is its ring system, a delicate structure stretching tens of thousands of miles around the equator. From a distance, the rings appear solid, like a smooth disk encircling the planet. In reality, They are made of countless pieces of ice and rock, each moving in its own orbit, with the entire structure so thin that if Saturn were scaled down to the size of a basketball, the ring's thickness would be comparable to a sheet of paper. A structure that is both vast and thin is another quiet illustration of how the universe favors combinations of grandeur and subtlety. The age of Saturn's rings remains an open question. Some models suggest they have existed since very early on, nearly as old as Saturn itself, remnants of material that never managed to coalesce into a moon. Other models suggest the rings may be much younger, only a few 100 million years old, the result of a moon torn apart by gravity and collisions. Both possibilities are still being considered, and no definitive conclusion has been reached. This makes the ring system feel like a temporary detail in Saturn's life. It may be something that has been there for a very long time, or it may be a relatively recent adornment in the planet's long history. On astronomical timescales, new and old sometimes differ only in how humans interpret the numbers. Around Saturn are also moons that feel very close to imagined scenarios of radically different environments. Titan is one of them. It is Saturn's largest moon, with an atmosphere thicker than Earth's, and a surface pressure about 1.5 times what humans are accustomed to. Temperatures on Titan's surface are so low that water freezes solid like rock, but methane and ethane can exist as liquids, forming lakes, rivers, and even seas on the surface. The hazy orange sky, the slow-flowing liquids, and the cold, dark shorelines create a world where rain and rivers still exist, but with entirely different substances. Titan is like an inverted version of Earth, where water becomes rock and hydrocarbons become flowing streams. Much smaller, but equally remarkable, is Enceladus, a bright, icy moon only about 313 miles in diameter. Its surface reflects most of the sun's light, making it appear like a small, cold sphere of ice. Yet observations from the Cassini spacecraft showed that near Enceladus's south pole are fractures that eject plumes of water ice into space, like geysers on Earth, but extending into a vacuum. Analysis of the ice particles and gases from these plumes indicates the presence of liquid water and some simple organic molecules. Beneath the thick ice shell, there may be a subsurface ocean in contact with a rocky core, where slow chemical reactions take place in the darkness. On such a small world, the idea of a hidden sea greatly expands the concept of what it means to be habitable, beyond what was once imagined based only on surface conditions. When looking back at this entire region, from the sparse asteroid belt to the giant gas planets and their rich moon systems, Earth begins to feel more distant in perception. It is not the largest planet, not the one with the most satellites. It has no extensive rings, and it does not possess storms that persist for centuries. In this picture, Earth is just one of many worlds orbiting the same ordinary star, with a size and position that are unremarkable when viewed only through numbers. Yet precisely as scale fades into the background, something else becomes clearer. The value of a world does not lie solely in its size or brightness, but also in what has happened on its quiet surface. Once accustomed to seeing even these giants as structures that are both immense and temporary under the sun's light, the journey can continue farther still. Beyond their orbits, the solar system stretches into regions where the sun's light and gravity gradually thin out, like warmth dissipating into cold space. There, the boundary between our system and interstellar space is not a sharp wall, but a transition zone where the sun's influence slowly blends into the background. And it is precisely where the sun's power nearly fades that the sense of how small everything inside it is, including the giant planets, becomes clearer than ever. Far beyond the orbits of the gas giants, where sunlight grows faint and cold, it seems as though the edge of the system has been reached. But what the naked eye might suggest is not the true boundary. Even if Neptune is considered the final gatekeeper, beyond it lie darker and colder regions, stretching vast distances, reaching close to the spaces between the stars. Before arriving there, one must pass two blue worlds at the outer rim, where rotation and seasons differ profoundly from those on Earth. Uranus is one of the strangest planets when it comes to how it spins. Its axis of rotation is tilted almost completely sideways, about 98 degrees relative to its orbital plane. Instead of spinning upright like a top, it rolls along its path, like a ball turning on its side. As a result, its poles take turns, pointing directly toward the sun and then away from it. Each hemisphere can experience more than 40 years of nearly continuous daylight, followed by more than 40 years of near-total darkness. A year on, Uranus passes slowly, and the seasons there are so long that a human lifetime would witness only a few transitions. Some hypotheses suggest that long ago, a collision with a massive celestial body knocked the planet over and left it frozen in this orientation ever since. Its magnetic field is also tilted, misaligned with its axis of rotation, causing magnetic field lines to twist in unpredictable ways. It is a large world, yet one that seems to drift through space with its head tilted in sleep, moving steadily along its long orbit. A little farther out lies Neptune, the outermost of the gas giants. It takes about 165 Earth years to complete a single orbit around the Sun. Since its discovery in 1846, Neptune has not yet completed two full orbits under the scrutiny of modern science. Its thick atmosphere is a deep blue, marked by faint cloud bands that move rapidly across its surface. Winds on Neptune are among the strongest ever recorded in the solar system, reaching speeds of roughly 200 miles per hour. When the Voyager 2 spacecraft flew past the planet in 1989, it captured images of a large, dark storm known as the Great Dark Spot. A few years later, when telescopes such as Hubble observed the planet again, that storm had vanished, replaced by new storms appearing in different locations. At such a distant and frigid range, the atmosphere continues to change, showing that even places assumed to be the most still possess their own slow and persistent motion. Orbiting Neptune is an especially remarkable large moon, Triton. It circles the planet in the opposite direction of Neptune's own rotation, a retrograde orbit unlike that of most natural satellites. This suggests that Triton may not have formed alongside Neptune, but instead originated farther away and was later captured by gravity into its current path. On its frozen surface, there are signs of geological activity, with plumes of material erupting from beneath the ice. Triton's orbit is slowly shrinking over extremely long timescales. Calculations indicate that in a few billion years, it may drift too close and be torn apart, forming a ring system around Neptune. Even at the edge of the solar system, where time seems stretched thin, there are silent shifts, moving toward new structures. Beyond Neptune's orbit lies a vast and cold region known as the Kuiper Belt. This area of space contains countless icy objects, ranging from small fragments to dwarf worlds, thousands of kilometers in diameter. The distances between objects in this region are still immense. There is no crowded field of debris like those imagined in fiction. These bodies preserve large amounts of ice, dust, and frozen compounds from the earliest days of the solar system, like an ancient archive of what remained after the major planets formed. Against the dark, cold background, individual chunks of ice continue their steady paths, like specimens never touched by any hand. Pluto lies within this region and is one of its most prominent members. Its diameter is about 473 miles, far smaller than that of the classical planets. At least 5 moons orbit Pluto, the largest of which is Charon, roughly half Pluto's size. The mass and distance between these two bodies place the system's center of mass in the space between them, rather than inside Pluto itself. As a result, Pluto and Charon resemble a binary system more than a typical planet and moon. Both revolve around a shared point, like two light bodies slowly circling one another in a prolonged, gentle dance. The sense of a single center fades. There is no fixed place that dominates, only a balance between two masses in space. When the New Horizons spacecraft flew past Pluto in July 2015, the first close-up images transformed how this small world was understood. Pluto's surface revealed towering mountain ranges made of water ice, standing firm like rock in extreme cold. Between the mountains lay plains of frozen nitrogen, smooth and flat, bearing traces of icy flows that once reshaped the surface. A thin atmosphere surrounds Pluto, extending outward, where faint layers of haze stack one above another. On the surface, a bright, heart-shaped region known as Tombaugh Regio rests quietly, an unmistakable marker on a distant world. All of these details show that even at the frozen edge, there are places where terrain and atmosphere continue to change, though everything unfolds very slowly. Farther still, beyond the Kuiper Belt, the idea of a boundary begins to soften. Astronomers believe the solar system is surrounded by a vast spherical region of countless small icy objects known as the Oort cloud. This region is thought to begin at roughly 2,000 astronomical units from the Sun and extend out to about 100,000 astronomical units, nearly 2 light-years. That distance is close to half the way to the nearest star. No object in this cloud has ever been observed directly. Its existence is inferred from the orbits of long-period comets, celestial bodies that quietly fall into the inner system and then drift away again. If it exists as imagined, the Oort cloud resembles a thin, icy shell enveloping the entire solar system, where the Sun's influence gradually blends into interstellar space. When viewed from the Sun out to the Oort cloud, the solar system is no longer a flat set of orbits as shown in simple diagrams, but a structure stretching trillions of miles in every direction. Earth sits at just 1 astronomical unit, about 93 million miles away, very close to the center compared to the outer edge. A common way to visualize this scale is the basketball model. If the Sun were the size of a basketball, Earth would be no bigger than a peppercorn placed several dozen steps away, while Neptune would need to be positioned so far out that an entire court would be required to show the distance. The Oort cloud, at the same scale, would lie far beyond the visible area, almost drifting into the darkness of another space entirely. At this scale, familiar numbers lose their ability to form clear mental images. The difference between 1 billion and 10 billion miles no longer feels distinct to intuition. What once seemed extremely distant in everyday life collapses into short segments along a much longer axis. Seen this way, the solar system is no longer a small planetary system that can be neatly framed in a few illustrations, but a region of influence that gradually fades into the emptiness between stars. When leaving the imagined shell of the Oort cloud behind, the next step is not a specific new place, but the space between stars. There, familiar measures such as astronomical units or planetary distances no longer apply. Light takes years to travel from one star to another. The Sun's gravitational influence grows very weak, gradually giving way to the pull of nearby stars. From that perspective, the solar system is just a small, bright region within a denser network of other systems, each with its own planets, moons, and empty spaces. And within that entire structure, Earth is only a small rocky grain, moving steadily at a distance that is very close when compared to the true scale of the system to which it belongs. At this stretch of the journey, distance begins to change its language. It is no longer spoken in miles or millions of miles, but in light years, and this is when intuition, accustomed to smaller numbers, gradually lets go. The star closest to the Sun is not a matter of a few billion or a few tens of billions of miles away, but about 245 light-years. A light-year is the distance light travels in 1 year, roughly 5.88 trillion miles. slowly multiplying those two numbers together. The distance to Proxima Centauri, the nearest star, comes out to around 25 trillion miles. The digits line up for so long that, at some point, the brain stops trying to reconstruct an image and simply accepts that this is very far. One way to preserve a bit of intuition is to shrink everything into a simple model. If the distance between Earth and the Sun, one astronomical unit, 93 million miles, is scaled down to exactly 1 inch on a ruler, then Proxima Centauri would be about 4 miles away from this model solar system. 1 inch represents the distance from a planet to its own star, and 4 miles represent the gap between that star and the next nearest one. Between those two markers, there are no additional planets, no additional stars, just sparse space with a few dust grains and rare particles of matter, with the scale set this way. The solar system looks like a small oasis on a map that is almost entirely blank. The spacecraft humans have launched so far also appear in this picture, but only in a very modest corner. Voyager 1, which left Earth in 1977, has been flying for more than 47 years, passing beyond the direct influence of the solar wind and entering nearby interstellar space. It has traveled about 15 billion miles at a speed of roughly 38,000 miles per hour. This is a very quiet but impressive achievement on the scale of human technology. Even so, if Voyager 1 were imagined to be aimed straight toward Proxima Centauri, which it is not, it would still need about 73,000 years to arrive. That number is so large that any notion of a human lifetime or even a civilization's span begins to blur. Over that time, languages, continents, and even the shape of the civilization that launched the probe could have changed many times over. Even if one assumes a future in which technology has advanced far beyond today, the basic picture does not change very much. If it were possible to build a spacecraft capable of traveling at 1/10 the speed of light, far faster than anything that exists now, the journey to Proxima Centauri would still take more than 42 years. Someone who set out in youth, assuming the trip went perfectly, would arrive having already lived through most of a lifetime. At this scale, the distance between stars is not only a technical problem, but also a soft limit set by biological time. The speed of light becomes a natural boundary for what it means to visit the neighbors in the universe. Proxima Centauri, the star in question, is not a copy of the Sun. It is a red dwarf, much smaller and far dimmer. Its diameter is about 129,000 miles, only around 14 to 15% of the Sun's diameter. Stars like this are the most common type in the galaxy, small, dim, and slow burning. The estimated lifetime of a red dwarf can stretch into the trillions of years. The universe, as currently understood, is not yet old enough for any red dwarf to have had time to burn out due to a lack of fuel. In this very long view, large, bright stars like the Sun are fast and hot-lived, while red dwarfs are small lamps that burn steadily against the dark background. However, that longevity does not mean they are gentle environments for nearby planets. Proxima Centauri is a flare star, prone to sudden increases in brightness over short periods caused by energetic eruptions on its surface. These flares release intense radiation that can damage the atmospheres of planets orbiting very close by. Proxima is known to have at least 2 planets, one of which, Proxima b, lies in what is called the habitable zone, where surface temperatures, given a suitable atmosphere, could allow liquid water to exist, but a planet being in this zone does not automatically make it a second Earth. Radiation from frequent flares can erode atmospheres, disturb surfaces, and make long-term stable conditions for complex life difficult to maintain. Proxima does not stand alone. It is part of the Alpha Centauri system, a triple star system bound together by gravity. The 2 main stars, Alpha Centauri A and B, form a pair orbiting each other, with masses and brightnesses similar to the Sun. Proxima, smaller and dimmer, moves on a much wider orbit, like a quiet member of this three-star family. The Alpha Centauri system therefore becomes a natural target when humans think about the first interstellar journeys. Yet with current technology, no spacecraft can carry humans there within a single lifetime. All plans remain at the level of ideas, simulations, or long-duration robotic missions. These distances keep the notion of going to the nearest star in the state of a distant horizon, always ahead, but never drawing much closer through desire alone. If the view is widened slightly beyond Alpha Centauri, a list of nearby stars begins to appear, each name attached to a number of light years. Barnard's star lies about 6 light-years away, another red dwarf, old and dim, drifting slowly across the sky. Sirius, the brightest star in Earth's night sky, is about 6 light-years away and is actually a binary system with a small white dwarf companion, Betelgeuse. A massive red supergiant in the constellation Orion lies much farther still, roughly 700 light-years away. All of these stars appear very bright from Earth. But if one stood at their locations and looked back, Earth would not stand out as a recognizable point. At those distances, the Sun is just one of many ordinary stars, and the light reflected from Earth is completely lost in that glare. The sense of losing a mental grip begins here. When talking about planets in the solar system, even though they are far away, the brain can still sketch a rough line. But when the discussion turns to 5 light-years, 10 light-years, or hundreds of light-years, any attempt to imagine a specific distance becomes meaningless. What remains is only scale. A few light-years is near. A few dozen is moderate. A few hundred or a few thousand is far. The rest, the space between stars, is mostly a place where light passes through without encountering anything of note. Once Earth becomes invisible, even from the distance of its neighbor stars, the story of its place in the universe shifts focus. It is no longer remarkable because of its size, brightness, or any special position on a star map. Its significance, if it has one, lies not in how it appears from afar, but in what is happening on the thin surface wrapped around its rocky core. From that surface, humans look outward and measure distances that force the mind itself to stop. And from that stopping point, the journey can continue into a new level of zoom, where individual star systems are no longer the subject, but structures even larger, where everything once called a system becomes just a faint dot in a picture vastly bigger than before. The stars you see in the night sky, whether a faint point of light near the horizon or a bright streak against the black background, are all part of the same stellar city. That city is the Milky Way. It is not a thin, delicate band like the one often shown in drawing, but a colossal structure, about 100,000 light-years in diameter, containing between 100 and 400 billion stars. Each of those stars is its own sun, which may or may not have planets orbiting it. Seen this way, the solar system no longer resembles a central structure, but instead becomes a very small point within a silent crowd of light. The Sun does not lie at the center of the galaxy, nor at its outer edge. It is located about 26,000 light-years from the galactic center, on a small branch called the Orion Spur, a protrusion from a spiral arm, like a quiet side street in the suburbs of a large city. There, the stellar density is moderate, not so crowded that the sky is always bright, and not so sparse as to feel empty. This position places the solar system away from the noisy central regions, where stars lie close together and high-energy events occur more frequently. In that context, Earth is orbiting an ordinary star, in an unremarkable suburban corner of a large spiral galaxy. To preserve some intuition for scale, one can shrink the distance between the Sun and Proxima Centauri, the nearest star, to 1 inch on a ruler. At that scale, the entire Milky Way would stretch about 2,000 feet, roughly the length of several city blocks, 1 inch for the distance between neighboring stars, and 2,000 feet for the entire stellar city. If the Milky Way were compressed further so that its full diameter measured only 100 feet, then the solar system, including the orbits of its planets, would be thinner than a human hair in that model, even if one tried to draw it. The pen stroke would be far thicker than its true size. At this scale, any attempt to mark Earth's position becomes little more than a gentle approximation. The Milky Way is a barred spiral galaxy. From the center, a bar of stars extends outward, and from the ends of that bar, spiral arms spread like slightly curved arms, wrapping around the core. The stars in the galactic disk do not rotate like a rigid body, but at different speeds, depending on their distance from the center. The Sun takes about 225 million years to complete one orbit around the galaxy, a galactic year. During that time on Earth, continents drift, climates change, and entire species can appear and disappear without ever witnessing a full cycle of this journey. One orbit around the galaxy is long enough for the entire picture of life on a rocky planet to change many times over. Looking back into the past from this timescale, the last time the Sun and Earth were in a similar position along the galactic orbit, dinosaurs were just beginning to appear on Earth. Those massive creatures were born, flourished, dominated the planet's surface, and then vanished, while the Sun had completed only a portion of its path around the galactic center. Other species, smaller but more complex, appeared afterward. From the perspective of the Milky Way, these changes resemble small ripples on the surface of a very slow-moving river, where the overall flow continues steadily, largely undisturbed. Near the center of the Milky Way lies a large bulge, with a diameter of about 10,000 light-years. There, stars are packed much more closely together, with densities far higher than in the galactic suburbs. If there were a stable planet near the center, and if someone stood on its surface, the night sky would not be dark like Earth's. The number of visible stars would be so great that empty space would be hard to find. Their combined light would merge into a continuous glow, like a permanent twilight that never fully fades. Instead of a few hundred easily visible stars, there could be tens of thousands or hundreds of thousands of points of light, making the very idea of a dark night sky feel unfamiliar. At the heart of this bulge, observations indicate the presence of a supermassive black hole known as Sagittarius A. Its mass is about 4 million times that of the Sun, compressed into a region of space small compared to the size of the galaxy. Most of the time, Sagittarius A is relatively quiet, with only occasional bursts of energy when gas or fragments of matter fall into its region of influence. Stars very close to the center orbit at extremely high speeds. One well-studied star, called S2, takes about 16 years to complete an orbit, and at its closest approach, it comes within about 11 billion miles of the black hole, moving at roughly 5% of the speed of light. These orbits are silent evidence of a very large mass concentrated in the dark region at the galaxy's center. The spiral arms of the Milky Way are not fixed lines, but regions where gas and dust are compressed, creating conditions for new stars to form. In these areas, one often finds young, hot, bright blue stars that live fast and die young in supernova explosions. The Sun does not lie directly within one of these spiral arms, but in an interarm region, where stellar density and the frequency of supernovae are lower. This location is considered relatively calmer for a life-bearing planet, as it is less often swept by extreme energetic events, at a distance far enough from the center and far enough from intense star-forming regions. The solar system enjoys a somewhat quieter environment within the galaxy's dynamic structure. Surrounding the galactic disk is a sparse stellar halo, extending out to about 130,000 light-years. In this region, globular clusters, ancient groups of stars bound together by gravity, move along orbits that do not lie in the main plane of the disk. Beyond that lies a dark matter halo, an invisible structure inferred from the rotational motion of stars and gas. This dark matter halo may extend out to roughly 600,000 light-years, enveloping the entire Milky Way. Around the galaxy also orbit smaller companions, dwarf galaxies, circling like faint attendants. The Large Magellanic Cloud and the Small Magellanic Cloud are the clearest examples, visible to the naked eye from certain locations on Earth as two faint, glowing clouds in the night sky. The Milky Way does not stand still in space. It is part of a small group of galaxies called the Local Group, which includes Andromeda, another large spiral galaxy, and many dwarf galaxies. Measurements show that the Milky Way and Andromeda are moving toward each other. In about 4.5 billion years, the two galaxies are likely to collide and merge. Despite the word collision, the chance of stars directly crashing into one another is very small, because the distances between them are enormous compared to their sizes. Instead, the orbits of many stars will be distorted, spiral arms will be blurred, and the two stellar disks will gradually blend into a larger elliptical galaxy. From a planet that might still exist at that time, the sky could be filled with long, luminous streams of stars, like slow-moving streaks of water across the surface of a vast lake. When all these layers are placed side by side, the number of stars, the size, the spiral structure, the stellar halo, dark matter, the satellites, and future motion, the solar system shrinks into a very small detail, difficult to preserve in any visual comparison. Earth, already insignificant compared to the size of the solar system, nearly disappears when we speak of the entire Milky Way. All metaphors involving basketballs, rulers, or strands of hair are merely gentle attempts to give the mind something to grasp, while the real structure itself far exceeds our capacity for direct imagination. From this point of view, what remains is not the exact position of Earth on a galactic diagram, but the awareness that this planet is part of a larger flow, where stars form and fade, spiral arms turn slowly, and galaxies drift toward one another in silence. When the Milky Way becomes too large to contain Earth within any simple example, the journey can move one step further. This time, it is no longer about a single galaxy, but about groups of galaxies, superclusters, and the long filamentary structures of the universe, where even the Milky Way itself is only a point of light within a far broader cosmic current. At this level, galaxies are no longer the final unit. They do not stand alone like isolated islands, but gather into small groups, then larger clusters, and then regions so vast that their motion no longer looks like separate points, but like slow currents in space. The Milky Way, with all the scales mentioned earlier, is only a very quiet part of such a family. Our nearest family is called the Local Group, a collection of about 50 galaxies bound together by their shared gravitational pull. Within this group, Andromeda, also known as M31, is the largest galaxy, containing on the order of 1 trillion stars, several times more than the Milky Way. Triangulum, or M33, is smaller, but still holds around 40 billion stars. The rest are dwarf galaxies, faint and small, orbiting the larger galaxies like distant cousins. Seen from the outside, the Local Group looks like a small cluster of bright coins lying close together in a wide region of space, each coin carrying its own disk of stars, gas, and distinct orbits. The Milky Way is not the sole center, just one of several large members in a structure compact enough to be called a group. The Local Group does not drift alone. It is one of many groups, clusters, and galaxies scattered throughout a larger region known as the Virgo supercluster. This region spans about 110 million light-years and contains at least 100 groups and clusters of galaxies similar to the local group. With a total estimated number of stars on the order of hundreds of trillions, each cluster within it holds hundreds, sometimes thousands, of galaxies. When trying to draw the whole thing on a sheet of paper, the local group would occupy only a tiny dot, Virgo, a much larger area, and the spaces between clusters would take up the rest. On this scale, a galaxy containing hundreds of billions of stars becomes just a detail within a much larger number. One of the most important galaxy clusters in the Virgo supercluster is the Virgo cluster, located about 54 million light-years away from us. This cluster contains roughly between 1,200 and 2,000 galaxies, ranging from bright spiral disks to large, dim elliptical galaxies. Among them, M87 stands out as a giant elliptical galaxy near the center of the cluster. At the core of M87 lies a supermassive black hole with a mass of about 6.5 billion times that of the Sun. In 2019, this very black hole was imaged by the Event Horizon Telescope network, producing the first image of a black hole's shadow from a distance that light takes tens of millions of years to cross. Subtle variations in light made it possible to infer the structure of a region of space far smaller, where gravity is so strong that light cannot escape. To keep intuition grounded, it helps to return to a simple image. If we imagine the Milky Way as a coin placed on the ground, with its entire disk of stars compressed into a thin circle, then the Virgo supercluster would be comparable in size to a city surrounding that coin. A small coin, just a few centimeters across, lying within an area tens of kilometers wide. Between the edge of the coin and the city limits are distances filled with buildings, roads, and open spaces. In this model, the Milky Way is only a small unit within a much larger space, where other coins, other galaxies, are scattered and move slowly under a shared gravitational field. Looking even farther out, astronomers use a new concept, Laniakea. This is the name given to a superstructure that includes hundreds of galaxy clusters and groups, including both the Virgo supercluster and the local group. Laniakea stretches about 520 million light-years across and contains roughly 100,000 galaxies. Rather than focusing only on the positions of individual galaxies, this concept arises from observing their velocities and directions of motion. When arrows representing motion are drawn, it becomes clear that galaxies in this region tend to flow in the same direction, like small drops of water sliding across a slightly tilted surface. In that sense, Laniakea is not just a loose collection, but a region where shared motion creates the impression of a slow but directed flow. The point toward which this flow appears to move is called the Great Attractor. It is not a single object, but a name given to a region of space where the total mass is large enough to create a significant gravitational effect, pulling galaxies in Laniakea toward it. This region lies close to the plane of the Milky Way in the sky, where dust and gas in our own galaxy obscure the view. Structures such as the Norma cluster, a massive galaxy cluster, are thought to be part of this attractor. We cannot clearly see every detail within it, but we can infer the existence of the Great Attractor from the way galaxies subtly tilt their motion toward a region on the cosmic map, like leaves slowly turning toward a gentle whirl that the naked eye cannot see. Farther still, at a distance of about 650 million light-years, lies the Shapley supercluster, another enormous concentration of galaxy clusters. With its immense mass, Shapley may be contributing to pulling all of Laniakea toward it, like a more distant center of gravity in the overall flow pattern. When Shapley is added to the model, the arrows of galactic motion no longer point toward just a nearby spot, but form a more complex directional network, where multiple massive regions simultaneously shape the paths of clusters and groups. On this scale, The local group, Virgo, and even Laniakea itself are merely details within a larger picture of dense regions of galaxies and the voids between them. Once everything is reduced to images of arrows and flows, the human view of the universe becomes lighter. Instead of trying to hold on to a single center, the new picture reveals a network where matter concentrates into nodes, connected by long filaments of galaxies. And between those filaments lie regions that are nearly empty. At this level, Earth, the solar system, and even the Milky Way become just points along a slow flow of space and time, drifting together with hundreds of thousands of other galaxies in a structure that the eye cannot fully grasp. As the view widens, single galaxies fade into patterns. Walls of galaxies appear, linked by long filaments, separated by immense voids where almost nothing remains. Farther still are regions whose light has not yet arrived. In that picture, what were once called systems, groups, or superclusters shrink together into faint patterns against a much broader background, where distance and density become the main lines shaping the observable universe. At this scale, the universe no longer appears as scattered points of light on a black background. When magnified far enough, those points begin to connect, forming thin lines, long strands, dense patches that resemble leaf veins. Between these luminous threads lie vast regions where there is almost nothing, stretching in silence across distances of hundreds or thousands of millions of light years. What we call the cosmic web is precisely this picture. A structure both delicate and so immense that any description of it is only provisional. This web did not appear suddenly. Very early after the Big Bang, the universe itself was not completely uniform. Some regions were slightly denser, others slightly more rarefied. Those tiny differences, over billions of years, were amplified by gravity. Where it was a bit denser, more matter fell in, gas accumulated, and galaxies formed. Where it was a bit thinner, matter was gradually pulled away toward nearby denser regions, leaving behind vast empty spaces, repeated again and again over an immense span of time. This process drew the luminous filaments, where galaxies line up, and the large walls, where galaxy clusters gather into broad sheets. What remains in between are the voids, regions that are nearly empty, where galaxy density is so low that light must travel a very long time before encountering another point of light. When humans began mapping galaxies at great distances, large-scale structures gradually came into view. One of these structures is the Sloan Great Wall, discovered in 2003. It is a band of galaxy clusters and groups stretching about 37 billion light-years. If one imagines each galaxy as an extremely tiny dot, then this wall is a long streak of such dots, connected along a particular direction. It is not a solid wall like those in everyday life, but a region where galaxy density is higher than the average background, extending across a distance that light needs more than 1 billion years to traverse. Within the fabric of the cosmic web, the Sloan Great Wall is only one part of a larger pattern. Farther still, deeper surveys have revealed even larger structures, such as the Hercules Corona Borealis Great Wall. Some estimates suggest that the length of this structure could reach around 10 billion light-years, a very large fraction of the radius of the observable universe. The existence of such extended structures has forced cosmologists to rethink how large-scale inhomogeneities form and evolve. At this scale, even theoretical models that work very well at smaller scales begin to be questioned. But in the context of the journey being told here, what matters is simply the feeling. There are extraordinarily long strands of the universe, where matter gathers into soft walls spread across space. Between these walls are the voids, regions much larger than any empty spaces at smaller scales. One of the more frequently mentioned voids is the KBC void, a region where galaxy density is lower than average. extending across distances on the order of 2 billion light-years. Not all of that region is completely empty. Rather, galaxies, there are rarer and more isolated. When viewed as a whole, voids are thought to occupy about 80% of the volume of the universe. This means that most of what exists at the largest scales is not galaxies, clusters, or walls, but space where there is almost nothing beyond a small amount of diffuse matter and thin radiation. What we see, the bright filaments and dense structures, is only the skeleton. The main content is emptiness. This entire picture lies within a region called the observable universe. The concept of observable here does not represent an absolute boundary of the universe, but a limit imposed by the speed of light and the age of the universe. The universe is estimated to be about 13.8 billion years old. Light can travel only a certain distance in that time. However, because the universe has been expanding while light is in transit, the diameter of the region from which we can receive signals today is not simply twice 13.8 billion, but about 93 billion light-years. In other words, the observable universe is a bubble within which light has had time to reach us. Beyond it, light is still on its way, or lies forever out of reach. Inside that bubble, observation-based estimates suggest there are about 2 trillion galaxies. Each of those galaxies may contain anywhere from a few hundred million to hundreds of billions of stars. Added together, the number of stars in the observable universe comes out to around 200 quintillion. That is, 200 times 100 quintillion, a number that is nearly impossible to fully grasp. A comparison sometimes used is with grains of sand. If each star were a tiny grain of sand, then the number of stars in the part of the universe we can see would be equivalent to filling an enormous number of giant swimming pools with fine sand. Such images are not meant to be exact. Only a small mental anchor when facing numbers far beyond everyday experience. Even with these numbers, human understanding of the universe still has soft boundaries. The actual universe may be many times larger than the observable region, or infinite. There may be structures similar to the cosmic web extending beyond the bubble we can see, with other walls, other voids, other flows. Some ideas in modern cosmology, such as eternal inflation or many worlds interpretations in quantum mechanics, suggest that multiple universes could exist, each with its own conditions. These ideas remain hypothetical and are difficult to test directly. But they remind us that the limits of knowledge do not coincide with the limits of existence. What we can measure, map, and describe is only a thin slice among many possible realities. At this scale, where the cosmic web stretches on, galaxy walls connect, voids occupy most of the volume, and the observable universe is just one bubble among broader possibilities. Familiar comparisons gradually lose their force. Numbers become labels rather than images. The mind, accustomed to miles, kilometers, hours, days, and years, has to stop before scales that even light needs billions of years to cross. And it is precisely at that stopping point that the journey can return to something very small, not small in an absolute sense, but small within this picture, a pale blue dot, orbiting an ordinary star in the outskirts of an ordinary spiral galaxy. From that dot, every map, every number, every model just described has been drawn. When the universe is zoomed out until everything becomes networks and voids, what humans can still hold on to is only the story of life on that dot, and the quiet meaning of existing there, for a very brief moment in a very vast universe. After traveling to places where Earth has almost disappeared from every measurement, the journey returns to a very familiar point. Not because it is large, but because it is where everything just described was conceived, measured, and named. The story comes back to a tiny dot, where humans live, love, argue, create, sleep, and dream. In 1990, when Voyager 1 had left the inner solar system, at a distance of more than 3.7 billion miles, it was commanded to turn back and take a photograph toward home. In that image, Earth no longer appeared as a sphere of clouds and oceans, but only as a pale blue dot, smaller than a single pixel, suspended in a faint sunbeam. The entire planet was wrapped into a point so small that a fingertip could hide it, floating among streaks of light and shadow. At that distance, all borders, all cities, all mountain ranges, all oceans merged into a single, indivisible point. Carl Sagan, when looking at that image, offered a reflection that was very simple yet profound. On that tiny dot, every king, every farmer, every hero, every cruel person, every religion, every ideology, every war, and every peace treaty has taken place. Every joy and sorrow, every fear and every hope, has existed only on that small point. From a cosmic perspective, conflicts that seem enormous shrink into delicate motions on the surface of a speck of light. This feeling is not meant to make life meaningless, but rather to serve as a gentle reminder that smallness can coexist with preciousness, not deny it. The human brain was not shaped to work with scales like these. It is accustomed to the distance between two houses, between two cities, between a coastline and a mountain range. When confronted with 5 light years, 100,000 light years, 93 billion light years, it needs scaled-down models. Examples involving basketballs, strands of hair, coins, cities. These metaphors help preserve some sense of structure. But at a certain point, even metaphors are no longer enough. There is a point at which the mind can only accept that it is very large and leave the remaining space to silence. In that silence, another question emerges. If the universe is so vast, containing so many stars and planets, then if there are other civilizations, where are they? This is what is commonly called the Fermi paradox. From the numbers of stars and potentially habitable planets, it seems that intelligent life should not be extremely rare. Yet, so far, all observations remain silent. There are different explanations. Complex intelligence may be very rare, occurring only under extremely specific conditions. Civilizations may tend to destroy themselves before they have time to spread. Speaking up in the universe may be dangerous, so anyone intelligent enough chooses silence. They may communicate in ways humans do not yet know how to listen to. Or more simply, the distances may be so vast that all signals disperse and fade before anyone can notice them. Behind that paradox lies a simple reality. Humanity has only one example of life to learn from. All organisms on Earth, from bacteria deep within rock to plants, animals, and humans, share a very distant common ancestor, expressed through the shared language of DNA, the exact mechanism by which non-living matter could form the first self-replicating systems, what we call the origin of life, remains an open question. Some argue that, given the right conditions, life may arise relatively easily. Others argue that life is an extremely rare event, so rare that even in a vast universe, it may occur only a few times, until a second sample is found beyond Earth. This question will remain as an unfilled gap. When the story is placed within Earth's own timeline, the sense of slowness becomes even clearer. Earth formed about 54 billion years ago. The earliest traces of life may date back to around 8 billion years ago. Multicellular life appeared much later, around 600 million years ago. The explosion of body forms in the Cambrian period occurred about 540 million years ago. Dinosaurs appeared around 230 million years ago and disappeared about 66 million years ago. Modern humans emerged only around 300 0,000 years ago. And recorded history occupies only a very thin slice at the end. If the entire history of Earth were compressed into a single calendar year, with January 1 marking the planet's formation, simple life would appear around March. Multicellular life would arrive around December. Dinosaurs would pass across the stage in the final days of December and leave before the last moment. Modern humans would step on stage around 11:56 p.m. on December 31. All written history, all empires, all revolutions, all modern cities would occupy only the final few seconds of that year. In that picture, the emergence of self-aware intelligence is a very recent event, like a brief flash at the end of a long film. Meanwhile, the universe that contains Earth continues to change on very long rhythms. The universe is expanding, galaxies drifting farther apart. The rate of new star formation slowly declines over time. There are descriptions of a degenerate era, in which stars gradually burn out, leaving only cold remnants, white dwarfs, neutron stars, and black holes. On even more distant timescales, theory suggests that even black holes may slowly lose mass through Hawking radiation, over timescales, reaching up to 100 years. At such numbers, all historical milestones, all geological epochs, all biological ages on planets are merely very short segments in a timeline with almost no fixed markers. For Earth itself, the near future in geological terms remains relatively stable. Over the next few million years, continents will continue to drift, climates will fluctuate, species will appear and disappear. But in about 1 billion years, the Sun, due to its internal nuclear processes, will gradually grow brighter and hotter. The increased heat may cause Earth's oceans to evaporate, the atmosphere to hold more water vapor, the natural greenhouse effect to intensify, and the planet's surface to become hotter and drier. Farther still, in about 5 billion years, the Sun will enter its red giant phase, expanding enough to engulf Mercury and Venus, and possibly incinerate Earth or leave it as a dead rock orbiting a remnant. Eventually, the Sun will collapse into a white dwarf, a hot core slowly cooling in the darkness. Within the brief span of humanity compared to those milestones, the question of the future is not only about climate or technology. If a civilization can survive long enough, it may find ways to leave Earth, set foot on other worlds, and build new homes around other stars. That expansion, if it happens, will still take place in a universe where distance always plays a limiting role, no matter how far it goes. Every ship, every colony, every new city will remain small compared to the larger structure in which it drifts. And precisely because of that, if complex consciousness is rare, its existence here, even for a relatively short time, carries a gentle kind of responsibility to keep that flame from going out too quickly in the part of the universe where it exists. As the circle closes, Earth returns to its proper size in the picture, insignificant in scale, yet special in another way. The value of this planet does not lie in being larger or brighter than other worlds, but in the fact that on its thin surface, life has emerged, along with consciousness, the ability to create art, music, language, gentle relationships, and ideas of beauty. From a pale blue dot seen from afar, it becomes home when viewed from within. Amid all the scales that exceed intuition, what humans can hold on to is very simple. There is a span of time in which consciousness is allowed to exist on this dot, allowed to look up at the sky, draw maps, tell stories, and then close its eyes. In the moment before sleep arrives, one can let the image of that pale blue dot drift slowly through the mind, like a small, peaceful point in an immeasurably vast universe, and accept that, no matter how small it is, it remains the only home within reach. After moving through scales, where Earth gradually shrinks into a small detail, then almost disappears among the vast structures of the universe, we return to a place that feels very familiar. Not because it is large, but because it is where all the questions we have just explored were first asked. In the image of the pale blue dot, Earth appears as a fragile point of light suspended in an immense darkness. And yet, on that tiny point, every human story has unfolded. Every joy, every fear, every hope, and every mistake has existed within that unimaginably small space. The vastness of the universe does not make life meaningless. Instead, it makes each moment of existence quieter and more precious. When everything is placed in its proper scale, there is no need to exaggerate or diminish anything at all. Thank you for accompanying me on this slow journey. And as you close your eyes, allow the remaining secrets, the quiet surprises of the universe, to keep waiting for the next exploration within the deep stillness of the endless cosmos.